Next topic in this chapter, what we have to discuss is about the kinetic molecular theory of gases. Kinetic molecular theory of gases. What is this theory? What for it is? What is the basis for this theory? What is its use? This is all what we have to discuss now. So far what we have discussed is the different gas laws to understand the behavior of gases. As at the very beginning we made it very clear that all the gas laws what we have discussed, whether it is Boyle's law, Charles' law, Avogadro's law, even Graham's law and Dalton's law, all these are the laws that are given by different scientists on the basis of the experimental data, experimental results what they obtained in their studies. So it is all based on the experimental results. Means at constant temperature for a fixed amount of gas it was observed that with increase in pressure volume is decreased. That is what practical, for how much increase in pressure, how much decrease in volume is taking place. This is what experimentally observed, and based on the results the graphs have been drawn. From the graphs the conclusions have been drawn, and those conclusions are only summarized as the different laws. So these are all experimental basis, but for none of these laws there is any explanation that why this is happening in the case of gases. What is the reason that at constant temperature for a fixed amount of gas with increase in pressure volume is decreasing? What is the reason? There is no explanation. Also in Charles' law, Avogadro's law, everywhere absolutely there is no explanation at all. It is all only experimental observation. But whatever may be the experimental observation, but for every observation also there should be a theoretical background. A theory should support it. That theory is even, the theory which supports all these gas laws is this kinetic molecular theory of gases. So this kinetic molecular theory of gases is a theory which explains all the gas laws and behavior of an ideal gas. Behavior of an ideal gas. Then why is it called kinetic molecular theory of gases? The reason it is called a kinetic molecular theory of gases is because this theory it is based on molecular motion, that is kinetics, in a gas. It is entirely dependent on molecular motion in the gases. How the different molecules are moving in a gas, in a given amount of gas under the given conditions. So because it all deals with the kinetic parameters of the gas molecules, kinetic parameters of the gas molecules. So is the reason that kinetic parameters of gas molecules, so it is called kinetic molecular theory of gases. That is the reason. Then what this theory says, first of all this theory is, it is certain postulates have been made, certain postulates have been made in this theory. That means certain assumptions have been made in this theory. What are those assumptions? The assumptions are, first of all, any gas consists of small tiny particles called molecules. If it is a case of noble gases, it is not molecule, it is atom. It is atom or molecule overall we can take. So, whatever with that particle of gas, either you call it as atom or molecule, that is even, right, that is quite known. In fact, not only gas, any substance is made up of atoms or molecules, that is in general, right. So, it is small particles called molecules or atoms. Now, second thing is, all these molecules are in continuous motion. All molecules are in random motion and no molecule will be at rest. At any given condition of temperature and pressure, no molecule of the gas will be at rest. All the molecules will be in continuous motion. They will be keep moving. No gas molecule will be at rest, right. Then the next assumption is that as all the gas molecules are here this is random motion. What do you mean by random motion? Random motion means the molecules are moving in random directions with random velocities. Velocity of different molecules will be different. Velocity of different molecules will be different and directions are also different. It is not necessary that all the molecules have to move with the same velocity. In a given amount of gas, if you have different molecules in the gas, this molecule moving in this direction, this molecule will be moving in this direction, this molecule will be moving in this direction, this molecule will be moving in this direction. The direction is not same for all the gas molecules. Similarly, the velocity with which the gas molecules are moving is also very less. This may be moving with velocity v1, this may be moving with velocity v2, this may be moving with velocity v3, or this may be with velocity v4. v1, v2, v3 may or may not be same. We cannot say anything. It may or may not be same. So, they are moving with different velocities in different directions. Then also certain molecules will have very low velocity, certain molecules will have very high velocity, certain molecules will have moderate velocity. It depends, right. And the next very important thing is, now because the molecules are moving in random velocities in random directions, there is every possibility that the molecule moving in this direction and the molecule moving in this direction will come close to each other and will collide with one another. So, there occurs intermolecular collisions. Intermolecular collisions will be taking place. Intermolecular collisions will be taking place. Means, as the molecules are moving in different directions, as I told, this molecule and this molecule, when they are coming in opposite directions, obviously they both will collide with each other. This is nothing but intermolecular collisions. Two molecules coming and colliding with each other. This is intermolecular collisions. As many molecules are there, all of them are moving in different directions. At some instant of time, the molecules will be colliding with each other. And one more important thing is, the collision is not only between different molecules, the collision also equally possible between a molecule and wall of the vessel. Collisions also will take place between molecule and wall of the vessel. Yeah, obviously, if the molecule is coming towards the wall of the vessel, obviously it has to collide on the wall, right. Now, here also the point is that all intermolecular collisions are perfectly elastic. All intermolecular collisions are perfectly elastic. All intermolecular collision, as two molecules are coming in opposite directions and colliding, this collision is an elastic collision. What is elastic collision? where the total energy is conserved. One molecule may gain energy, one molecule may lose in its energy, but total energy change is 0. Neither energy is average energy will remain the same. One molecule, because when the two molecules are colliding, the velocity of one molecule may increase, velocity of another molecule may decrease, but net difference will be 0, right. So is obviously the kinetic energy, right. This is what we call elastic collision. But remember, the collision between the molecule and wall cannot be an elastic, because the molecule being stationary. The molecule being stationary, when it comes and hit, it will exert certain force. So, due to collision between molecule and wall, certain force is exerted by the molecule on the wall, and that force exerted per unit area is what we call pressure. Force exerted here, what one postulate of this kinetic theory says is that the pressure exerted by gas is due to collision between the molecule and wall. Why the pressure is only between collision? Why the pressure is only due to the collision between the molecule and wall? The reason is simple, that during intermolecular collision it is elastic collision. There is no change in the total energy. But for a collision between molecule and wall, as the wall being stationary, the molecule come and hits on the wall. So obviously it exerts certain force. Just like when you hit a ball on the wall, the ball comes back with certain force, and that is what is nothing but we will say the ball exerts certain force on the wall. So that force exerted by the molecule on the wall is nothing but, that per unit area is nothing but pressure. So is the reason, one simple thing what you should understand is that pressure exerted by the gas is only due to collision between the molecule and wall of the vessel. And another very important postulate is that the volume occupied by gas molecules is negligible compared to total volume. Means here you have many molecules, but as you can see with the way that we have drawn, there is a huge gap between different molecules. One molecule at one end, the other molecule at the other end, there is wide distribution, right. So in general, now if you take each molecule of volume V1, V2, V3, etc., then, and this total volume is nothing but what? Volume of the vessel. V1 plus V2 plus V3, volume of gas molecules will be very much less than V. This V is the volume of the vessel. Some of the volumes of each molecule with the radius of 1 angstrom or 1 picometer, 4 by 3 pi r cube, that will be the volume. Add all those volumes. This volume is say 1 liter, 10 liter or something, is very high compared to that 1 angstrom or 1 picometer. Basically the meaning is that if you take a gas in a vessel, there exists large empty space. Large empty space will be left at in the vessel. So there exists a large gap, the large empty space in the vessel. That is what the meaning. Volume occupied by the gas molecules is negligible as compared to total volume. Total volume means volume of the vessel, right. And other things also are there. These intermolecular collisions are not affected by gravity. Gas molecules, the molecular motion the molecular motion is not affected by gravity. As you know very well, in the air we have nitrogen and oxygen. Nitrogen and oxygen gases are completely in collision. There is a large amount of gas, large amount of air, but you know very well that none of that nitrogen and oxygen molecules are not falling down. If they are affected by gravity, obviously that all has to be come down and we will not have air in the atmosphere. That practically we all of us know that nothing of that sort is happening. What is the meaning of that? The molecular motion of the gas is not affected by gravity. So they are not falling down. And also another thing, kinetic energy of gas molecules directly proportional to absolute temperature. Kinetic energy of gas molecules, another very important, kinetic energy of gas molecules is directly proportional to absolute temperature. Molecular velocity is directly proportional to absolute temperature. With increase in temperature, kinetic energy of the gas molecules will increase. With a decrease in temperature, kinetic energy decreases. This is normal, straightforward principle of effect of temperature on the kinetic energy that already we people know. So these are the set of postulates that are given by the kinetic theory of gases. Based on this, all the gas laws have been proved. Based on these postulates, one equation called kinetic gas equation is derived. Using that kinetic gas equation, all the gas laws have been proved, all the gas laws have been explained, and the complete theoretical background necessary for all the gas laws in totality is given by this kinetic molecular theory of gases. Now, as just now I told, using all these postulates, using this kinetic molecular theory of gases, based on the postulates made in this kinetic molecular theory of gases, a mathematical equation is derived, another equation is derived, that is what we call kinetic gas equation, kinetic gas equation. For this, a gas consider a gas enclosed in a cubic vessel of length L centimeter. So when you consider a cube of length L centimeter, obviously volume of this is equal to L cube. Volume of that cube is obviously L cube. Now in this, consider a molecule moving with a velocity with certain velocity Cx. What do you mean by Cx? Its velocity along the x axis, the velocity of the gas molecule along the x axis. Then in the opposite direction it will be minus Cx. Okay. So like this when you consider, then this molecule, particular molecule under consideration, will go and hit the wall of the vessel, then to make successive collision on that particular wall again, this particular molecule has to travel a distance of 12 centimeter, because from here it has to go back to the other opposite end and it has to come. So from this side to the opposite side to move, the distance it travelled is L centimeter, from there to back again onto the same wall another L centimeter. So total distance that it travelled is 2 L centimeter, right. In this 2 L centimeter of travelling, then the momentum that it exerts is mcx, and the positive and the opposite side it is minus mcx. So the net change is 2 mcx. So what I mean to say is that if Cx is a mass of a gas molecule is m, mass of gas molecule is m, then momentum of the molecule, momentum of gas molecule is mcx to move in a one particular direction, then in opposite direction it is minus mcx. Therefore, change in momentum between two successive collisions on same wall by one molecule is 2 mcx, mcx minus of minus mcx, which is equal to 2 mcx, right. This is the momentum. Now, so when this is a momentum, then the number of this is the change in momentum for two successive collisions on one particular face, on one particular wall by one single molecule. Then if Cx is the velocity and L is the distance, then the time taken is L by Cx for two successive collisions, time taken between two successive collisions, right, that is the time taken. Then therefore, number of collisions per unit time will be Cx by L. Number of collisions will be Cx by L. Therefore, net change in momentum for all such collisions will be equal to 2 mcx into Cx by L, that is 2 mcx square by L, right. 2 mcx square by L is the net change in momentum. Then what is the force that it exerts? Then force exert is equal to force exerted between all such successive collisions is equal to force exerted is nothing but change in momentum is nothing but, so force exerted change in momentum is nothing but the force, so that is 2 mcx square by L. Now based on this, now pressure exerted then will be equal to 2 mcx square by L into 1 by L square, that is force by area, which is equal to 2 mcx square by L cube, right. And this is the what pressure for one gas molecule to move between the two walls along the x axis. Now if you take all the such axes, then the pressure for on all the walls, if you consider 2m by L cube into Cx square plus Cy square plus Cz square, which is equal to 2 mc square by L cube, right. For that means when it is the velocity is being given in all the three directions. Now this L cube is nothing but 2 mc square by L cube is now if you have This is for one molecule. Now for the collision to take place, at least what you require is two such things, and then for all such gas molecules, the net force, the net pressure exerted will be equal to 2 mn c square by L cube. Now this 2 mn c square by L cube, 2 mn c square by L cube. Now for a bimolecular collision, it is P equal to, now this is L cube is this is so 6 L cube, then because total it is 6 L square, when this is 6 L cube, so this I can write it as 2 mn c square by 6V, which in fact I will write it as PV is equal to 1 by 3 mn c square. Here L square is the area of one single phase, 6 L square is the total area of the cube, force per unit area, force per unit area. So when you are taking this force by area, total area is 6 L square, so it is 2 mcx square by 6 L cube. All the three directions, when the velocity component is resolved into all the x, y, z directions, the net velocity square c square is equal to cx square plus cy square plus cz square, right, by vectors we know. So that I am writing it as c square. This is the pressure exerted by one single gas molecule, pressure exerted by one single gas molecule between two successive collisions on one phase along the x axis and then along all the three axes, right. Now L cube is nothing but volume of the cube, so that I am writing it. So it will be 2 mn c square by 6 L cube, and this is the equation. This equation is what we call kinetic gas equation, right. Based on this kinetic gas equation, now we can prove all the gas laws that we see it now. Okay. So the kinetic gas equation is PV equal to 1 by 3 mn c square. P is the pressure, V is the volume, m is the mass of the gas molecule, n is the number of molecules, c is of course the velocity. This velocity we call it as RMS velocity. What is this RMS velocity? That I will define it later. Okay. So this PV is equal to 1 by 3 mn c square. Now from this what we can derive is, the very first thing is kinetic energy of gas molecules. Kinetic energy of gas molecules. Now as PV is equal to 1 by 3 mn c square, this I can write it as 1 by 2 into 2 by 3 mn c square. So 1 by 2 mn c square is obviously nothing but it is like 2 by 3 half mn c square the other way. Half mn c square is nothing but kinetic energy. Kinetic energy of all the gas molecules. If n is equal to 1, that is for one gas molecule. N is the number of molecules. C is RMS velocity, or simply velocity for the time being you can take. M is mass of gas molecule. So m c square is half m c square is kinetic energy for n is equal to 1. then Mn c square is the, and half Mn c square is total kinetic energy. Half Mn c square is total kinetic energy. So, this I will write it as 2 by 3 Ke, this is total kinetic energy. Therefore, kinetic energy is equal to 3 by 2 PV, or kinetic energy is equal to 3 by 2 nRT. And for 1 mole of a gas, kinetic energy you can write it as 3 by 2 RT, right. And also what we can write is kinetic energy per molecule, you can write it as 3 by 2 R by NEAT, or average kinetic energy is equal to 3 by 2 KT, where K is what we call Boltzmann constant. Where R by N, R is gas constant, Na is Avogadro number 6.023 into 10 power 23, that is Boltzmann constant, where K is Boltzmann constant. So, what is the difference between this and this? This is kinetic energy of all the gas molecules in the gas, given amount of gas, total kinetic energy. This is kinetic energy per molecule, that is average kinetic energy divided by Avogadro number, right. So, that in total if you take from these two, this is dependent on number of moles as well as the temperature, but average kinetic energy depends only on temperature. It is irrespective of whatever may be the gas it is. It is irrespective of whatever may be the number of moles in it is, because it is per molecule. Average it is. Therefore, whether you take 1 mole of sulfur dioxide or 1 mole of carbon dioxide or 1 mole of oxygen or whatever may be the gas that you take, or 5 moles of carbon dioxide, per molecule it is always the same. So, average kinetic energy of sulfur dioxide, carbon dioxide, oxygen or any other gas is same at same temperature. It varies only with temperature. If temperature is increased, obviously kinetic energy also increases, as Ke is equal to 3 by 2 Kt. But it is independent of number of moles, because it is per molecule. One molecule at same temperature, irrespective of whatever may be the gas it is independent of the mass. Here you do not have the mass term, or here you do not have the number of molecules term or anything. So, it is constant at constant temperature. This is an important one. So, this is the total kinetic energy, this is kinetic energy per molecule for any gas, which we derive it from this idea, this kinetic gas equation. This kinetic gas equation, which is derived, as we have discussed now, from the postulates of kinetic theory of gases, is for all numerical purposes it is exactly same as PV is equal to nRT, that is the ideal gas equation. This is also, we can consider it as another form of ideal gas equation, but derived from theoretical background. So, it is, they both are, it is also an ideal gas equation. Now, from this equation and from the term of kinetic energy and all, now we prove the gas laws again, right. That next we are going to discuss. Now, Boyle's law, if you want to prove from this, it is very simple, that PV is equal to 1 by 3 Mn c square. So, from this, as already that we have written, this PV is equal to 2 by 3 kinetic energy, right. PV is equal to 2 by 3 kinetic energy, as already we have seen, right, because kinetic energy is equal to half Mn c square. Therefore, and kinetic energy is proportional to temperature, or in other words, at constant temperature kinetic energy is also constant. Therefore, PV is constant at constant temperature. This is what is nothing but PV is constant is nothing but Boyle's law, right. So, Boyle's law is proved. Then when it comes to Charles' law, as PV is here in the Boyle's law, PV is constant. Now again the same thing, if you take as a PV is equal to 2 by 3 kinetic energy, or PV is proportional to kinetic energy, and kinetic energy is proportional to temperature. So, PV is proportional to T. Therefore, at constant pressure V is proportional to T. At constant pressure V is proportional to T is nothing but Charles' law. So, again Charles' law is proved. Then Avogadro's law, PV is equal to 1 by 3 mnc square. Then at constant pressure, if number of moles are N1 and volume is this is for Avogadro's law, PV is equal to 1 by 3 mnc square. At constant pressure, PV1 is equal to 1 by 3 m1 n1 c1 square. PV2 is equal to 1 by 3 m2 n2 c2 square. Then V1 by V2 is equal to m1 n1 c1 square by m2 n2 c2 square. m1 n1 c1 square by m2 n2 c2 square. At constant temperature, kinetic energy is constant. That means V1 by V2 is obviously equal to N1 by N2, because at constant temperature mc square is constant, because half mc square is kinetic energy. So, m1 c1 square is nothing but 2 into kinetic energy. At constant temperature, kinetic energy is constant. So, m1 c1 square by m2 c2 square will be constant. So, when this product is constant or this product is same, V1 by V2 is equal to N1 by N2. This is what the Avogadro's law, Boyle's law, Charles' law, Avogadro's law. All the basic 3 laws have been proved using this, what you call the kinetic gas equation. Then another very important law what we told is diffusion of gases. R1 by R2 is equal to root over M2 by M1. R1 by R2 is nothing but, obviously here directly you can see that mnc square. So, at constant pressure and volume, the rate of diffusion of a gas is inversely proportional to its density, or inversely proportional to square root of its density, or inversely proportional to square root of volume. So, this is, if you look at it, Graham's law. What Graham's law says is that at constant pressure and volume, rate of diffusion of a gas is proportional to 1 by square root of m, that is molecular weight. Rate of diffusion, R is nothing but velocity, rate is nothing but velocity. Therefore, according to kinetic gas equation, at constant P and V, 1 by 3 mnc square is constant. That means mc square is constant for n is equal to 1. Therefore, c square is proportional to 1 by m, implies c is proportional to 1 by root m. The c is nothing but velocity, or which is nothing but rate. So, proportional to 1 by root m. So, this is again R, C1 by C2 is equal to R1 by R2 is equal to root over M2 by M1. C1 by C2, that is ratio of velocities, which is nothing but ratio of rates of diffusion, is equal to square root of M2 by M1. That is what is nothing but Graham's law, right, which already we discussed in the previous lectures, right. So, like this, from the kinetic gas equation, kinetic theory, all the gas laws which we have discussed on the basis of experimental findings of different scientists also have been proved theoretically. So, finally, theoretical and experimental verifications have been completely made to all those gas laws. So, in totality, now all these laws together will give us the behavior of ideal gases. Now, here this, when it comes to velocity, every time we are saying it is a velocity, but here one point we told in the postulates of kinetic theory is that all gas molecules are not possessing same velocity. Different molecules are having different velocities. Some molecules are having very low velocity, some molecules are having very high velocity, some molecules are having moderate velocities. Then giving a uniform velocity for all the gas molecules is something not correct. So, in order to explain that, different types of molecular velocities have been proposed by scientists. So, what are the different types of molecular velocities that have been proposed in the gas for all the gas molecules in a given amount of gas is something we have to study under the heading of molecular velocities.